another deep dive episode of the Total Space Network. I'm Mikko, and today we have a special guest. But first, I will let the other hosts introduce themselves.
Hi there, I'm AnotherSpaceNut, and thank you for checking us out today, guys.
And we have Graham Lau. Would you introduce yourself?
Yeah, absolutely. First off, hi everyone. It's a pleasure to join all of you here on Total Space Network. My name is Graham Lau. I go online sometimes as the Cosmobiologist, and I'm an astrobiologist and communicator of science. My academic background, I started off studying biology and chemistry and wasn't quite fulfilled there, and so I started studying astrophysics, and then before I knew it, I had a PhD in geology, so I jumped around a lot in the sciences. My primary interest, though, scientifically has always been how can we understand what life does here on Earth, and how can we look for signs of life elsewhere in the universe? And along the way, during the time of earning my PhD, I discovered that I really enjoy the process of sharing science and sharing our knowledge with other people. I was always that guy who would love to sit around a campfire with a bunch of friends, having some beer and talking about, the stars over our heads and the beauty of the cosmos and some of the crazy things that we know and some of the things that we really don't understand right now. And so that kind of led me then, after my PhD, to really focus a lot on sharing science, on communicating science with communities around the world.
Great. And lately, we've been hearing news about Venus and the possible phosphine finding. Would you go over the latest news about it and how it will affect us if it's actually there?
Absolutely. The phosphine, I'll call it issue right now. Maybe even phosphine debate is better for what's going on right now in the scientific community. So hopefully everyone watching or listening knows earlier this year, a paper came out in Nature Astronomy suggesting that they had made detections of the molecule phosphine in the upper atmosphere of Venus, actually in the region of Venus's atmosphere where conditions are far more clement for life as we know it, where the temperature, the pressure is actually more like we have here at sea level on Earth, and not down on that blistering hot surface of Venus with very high pressure. The detection was made using two different telescopes. One was the James Clerk Maxwell telescope in Hawaii. This is a radio telescope, and they were looking for a radio detection of molecules in Venus and found this one little band in their spectrum that looks like the molecule phosphine. Later, they used another far more powerful telescope called ALMA. That's in the Atacama Desert down in South America. ALMA is the Atacama Large Millimeter Submillimeter Array telescope for those who aren't following. It's really worth looking into. It's a beautiful instrument and gets much higher resolution data than James Clerk Maxwell. And with this ALMA telescope, they looked again at Venus using these radio waves, and they were able to see in the spectrum that same single dip that looks like it could be the molecule phosphine. And so this led to that article where they suggested phosphine is in the atmosphere of Venus. One of my colleagues from our research institute called the Blue Marble Space Institute of Science is a co-author on that paper. And so I reached out to him that day. The paper was released and we had a conversation about their findings. And he said, the first thing to do is to confirm it's actually there because they only have a single band finding. So that's not really great. There's not multiple places where they find information suggesting phosphine. It's just one line of detection. And it's in the same region where some other molecules could be causing that line. For instance, sulfur dioxide also has a potential band right in that region that could be produced in Venus. And we know Venus has a lot of sulfur in its atmosphere, specifically sulfuric acid, but sulfur dioxide as well. And so it could actually be that and not phosphine. And that paper, for those who haven't been following, it had a lot of backlash, not just amongst the public, maybe who thought it would be some kind of bigger finding or really didn't understand what was being shared because journalists were like, we found life on Venus, which really wasn't the case. But also amongst scientists, scientists are just as fallible and just as likely to get angry about things as other people. And so there were a lot of scientists who rather than just attacking the science, also attacked the scientists who wrote the paper, which I thought was very unfortunate. That's not how we do good science. But fortunately now, after that, now we actually have some good science occurring where other people are writing papers, they're reanalyzing those original data, and they're also trying to figure out if the phosphine really is there. How could it be there? And how can we detect it further using other instruments besides just radio telescopes here on the Earth? And so there's a few things that we could do there. Bepi Colombo, which is flying to Mercury, it just had a flyby of Venus, but wasn't in the right position to really look for phosphine. And even though that instrument, that spacecraft wasn't made to look for phosphine on Venus, it has a second flyby on its way to Mercury. It will fly by Venus again in the middle of next year. And on that flyby, it could take a look and potentially see this phosphine. Also, the private company Rocket Lab right now is working on their own spacecraft to go to Venus, and they are very into this idea of having an instrument to look for phosphine on Venus if it's there. So that'd be really cool.
I was just saying, we love Rocket Labs at Total Space.
Yeah, I mean, it's really groovy what we're doing with private space right now. We still call it new space, even though it's been new for quite some time now. But all of these movements right now for commercialization of space, for more companies to compete with each other, to develop better rockets and better systems, better off-the-shelf hardware for space exploration, which brings prices way down. So Rocket Lab is one of the many who are doing awesome things to really open up space exploration for the rest of us.
Yeah, totally. Did Bepi Colombo try to get some data with the first flyby? Do you know about that?
You know, I actually do not know if they tried. I don't think they were planning to. From my understanding, based on the orientation of the spacecraft, at that time when it was flying by, it wouldn't have been turned in the right way anyway to look for phosphine if it were there. I could be wrong, though, and so it's worth reaching out to some of the researchers on Bepi Colombo to see if that was possible.
Yeah, for sure. I've been trying to keep up with the news, but I haven't seen anything about it. If the phosphine finding would be true, what would it mean for us?
There's one thing that I love to point out about Venus. First off, for everyone, I often say this, that Venus, if we go back in the history of our solar system, say you were an alien civilization and you traveled here 3.5 billion years ago, and you wanted to see which planets had life on them, I think Venus was far more likely the other candidate for life besides Earth, far more so than Mars in the early history of our solar system. And Venus may have had oceans. There's good modeling to suggest it might have had oceans, maybe even a more clement atmosphere long ago. Of course, having lost that since then. But if there was a biosphere on Venus that could have been preserved and could be causing this phosphine, that by itself is incredible. If there's alien life causing the phosphine in the Venusian atmosphere, that gives us a sign of alien life here in our solar system to go explore and learn more about. But honestly, I think the most important thing about this potential for phosphine in Venus is actually what it can help us to learn about exoplanets. So the same team, many of the people who are involved in this paper who suggest this finding of phosphine on Venus have also been involved in other papers suggesting that phosphine could be a biosignature on alien worlds far away. So if we look at exoplanets around other stars and we find a molecule like phosphine, right now a lot of people have thought that that could be a sign of life. But if we do have phosphine in Venus's atmosphere, and we discover that it's not made by life, so there could be various other photochemical processes, processes from volcanism at the surface of Venus, maybe something that we just don't understand yet going on geochemically or physically in the Venusian atmosphere to form this phosphine. That means that the phosphine itself then could also be a false positive for life. That if we look at an exoplanet far away and we find phosphine, it might not be a sign of life. And so this is really, really important for us to know. It's good for us to know what things might give us a false conclusion of a positive or a negative result for finding life on exoplanets. Because with Venus, we can go there. You know, we can send Bepi Colombo on its second flyby and take a look. We can send Rocket Lab. Other missions are going to come around now, thankfully, to go to Venus. And I think this paper will stimulate more support for going to Venus. So from like Da Vinci Plus is a really cool mission that could go to Venus, currently in the concept phase. And I know other organizations are looking at some Venus missions as well. We can go there and test this. If the phosphine really is there and we confirm its presence, we can go figure out why it's there and if it's life or not. And that will help us then looking at alien worlds far away to figure out if there's life there as well. And an important thing to remember is that gas giants like Jupiter and Saturn also have phosphine. And we actually have really good models for how that phosphine can form abiotically without life. And so when we're looking at these alien worlds far away, we need to figure out, is this phosphine formed like it's formed on Jupiter and Saturn? Is it phosphine being formed maybe how it's being formed on Venus, whether or not that's life? And so these are really important things for us to test. When I was born, I mean, we had 0 other planets beyond our solar system that we knew about for sure. People for centuries and millennia had been predicting that other worlds existed, myriad worlds out there beyond our solar system. And it's only really since the mid-90s that we've been discovering all of these exoplanets. And it's well over 4,200 exoplanets now that we know of. And I have a feeling by the time I'm quite an old man, that number will skyrocket up to 100,000, maybe 200,000 or more. And so that really opens up the window for finding potential alien life beyond our solar system.
There was a recent paper published on white dwarfs, and that was to focus on exoplanets as well. What do you think this find of phosphine in our own solar system might help us when the James Webb's in operation, searching for future exoplanets and, trying to find life out there?
Yeah, again, it's about what we can actually do from Earth. And from Earth, we can't send spacecraft very quickly to these other stars to go explore those exoplanets. And so we are very much stuck using telescopes, and they've really opened up the universe for us in various ways. James Webb Space Telescope is going to be incredible if and when we finally launch the thing. Obviously, it's been very long delayed, and it's way over budget, but it's going to be an awesome mission once we actually launch it and get it out to its orbital point beyond the moon and start using it for some real science. And one of the best things with James Webb is that when it comes to looking at exoplanets, is that it will be able to look at the spectra coming through those little bits of atmosphere of exoplanets from so far away better than anything else we've ever had before. And so James Webb will help us to really start looking chemically what is in the atmospheres of these exoplanets. And so that's when we can start looking for potential biosignatures, potential molecules that could be produced by life, and also looking for the different mixtures of chemicals, looking for things like disequilibrium in the chemicals. And who knows, there's also the idea that we could find technosignature molecules. So here on Earth for a long time, we were producing CFCs or chlorofluorocarbons in aerosol sprays and air conditioning and stuff like that. And we saw that it was causing a hole in our ozone layer to form. And in what was actually a really beautiful process of governments finally working together a little bit, we signed a Clean Air Treaty, a Clean Air Act that many nations signed on to get rid of these CFCs. But chlorofluorocarbons are not produced naturally in the environment. They are an industrial molecule. And so maybe we'll look at exoplanets using James Webb Space Telescope in a few years ahead of now, and we'll see some of these potential signs of industrial activity on alien worlds far away. And so maybe our first detection of potential alien life won't be from finding biosignature gases and maybe from like large-scale microbial biospheres, but instead will be from intelligent extraterrestrial civilizations.
Yeah, that would be great. Did you read the news about some weird molecule in the atmosphere of Titan?
Yeah, I have. So Titan is really cool. So I have a show called Ask an Astrobiologist, run through NASA Astrobiology. I had Melissa Trainer on my show recently, and it was really just wonderful to talk with her. She's the deputy principal investigator for the Dragonfly mission. So for those watching and listening, if you don't know, we actually have another mission going to Titan. So we had the Huygens lander, so it went along with the Cassini spacecraft to Saturn. Not long after Cassini got into the Saturnian system, we launched off this lander called Huygens, which went down and went through the atmosphere of Titan and landed on the surface. But Huygens was really designed just for that descent part of understanding Titan. We didn't know what we were going to land on, if it'd be fluid or gunk, or if the spacecraft would just sink down into the surface. And so it really wasn't designed for surface activities. But Huygens gave us a lot of really great information about Titan's atmosphere. And we've also done a lot, from using ground-based telescopes here on Earth, space-based telescopes in orbit, to look at Titan, to understand its chemistry. And when you look at this giant moon of Saturn, you see a really thick atmosphere. It's so thick in extent where the International Space Station is orbiting around the Earth in low Earth orbit. If you were to orbit a space station around Titan in that same area, you'd still be very much inside of the thick, hazy clouds of Titan. Titan's atmospheric pressure isn't too much more than us. It's only 1.5 bar at the surface. It is extremely cold on Titan. very close to the temperature of liquid nitrogen. So it's very cold in the surface. But the cool thing about Titan is that its atmosphere and even its surface is full of organic molecules, a bunch of hydrocarbon goop. And so we have here on Earth a hydrological cycle. We have water in rivers and oceans and lakes that evaporates up into the atmosphere, and it can condense and make clouds and then precipitate back down as rain and snow and sleet and hail. And Titan has a very similar process occurring, but we call it a methanological cycle. And in this methanological cycle in Titan, methane and ethane, hydrocarbons with 1 or 2 carbon molecules in lakes on the surface of Titan are evaporating into its atmosphere, making this thick haze. But that haze is also then being reacting with sunlight. And even though Titan is very far away from the sun compared to where we are, the sun would be very dim compared to what we're accustomed to at the orbit of Saturn. And yet that little bit of the energy of the sun coming that far can react with these molecules in the atmosphere of Titan. And it can create all kinds of reactive molecules that react back together and make things like benzene, for instance, a 6-carbon cyclical structure. And then more recently, some researchers, including Connor Nixon, discovered a very rare molecule, which I might get the name wrong here. It's Cyclopropylinidine is the name of the molecule. It's a 3-carbon molecule. And so these three carbon atoms come together into a triangle structure, and then one of them has 2 of them have a hydrogen molecule sticking off the side. So it's C3H2. This molecule does not form anywhere on Earth terrestrially. We can only form it in the laboratory to learn more about it here on Earth. However, it has been found all over in the universe. When we look out with our telescopes into the interstellar medium, into the dust clouds and material out there in space in our galaxy, we've actually seen this 3-carbon triangular molecule inside in these dust clouds in space. But those clouds are very diffuse. The molecules aren't very close together. And this molecule, this cyclopropylinidine, is very reactive, which is why we don't have it here on Earth in terrestrial environments. It would react with everything else around it. In the interstellar medium, there's not much stuff, so it's not reacting. Whereas in Titan's atmosphere, there is a lot of stuff. It's a very thick, hazy region in the atmosphere. And so this molecule might actually be reacting with other things. But again, it's also very cold. And so that lower temperature probably also helps kinetically hinder some of those reactions. But it's still very intriguing to find a molecule like that. The same team who found this weird molecule in Titan's atmosphere, they were also looking for things like purines and pyrimidines. These are other cyclic molecules with carbons in cyclical structures. But in the case of purines and pyrimidines, those are molecules that form the basis of our DNA and RNA for life as we know it here on Earth. And there's actually a large number of molecules that have been discovered in Titan's atmosphere from these photochemical reactions, and it's raining back down onto the surface. It's making, a sandy structure of organic gunk all over. Like I mentioned, I had Melissa Trainer on my show, and it was really cool to hear, her perspective of the successes of Huygens on Titan, but also the reasons why we're now sending Dragonfly. So again, when Huygens landed, it really wasn't intended to live on the surface and take scientific measurements for any prolonged period of time. Whereas the Dragonfly mission is a really cool drone that's going to land at the surface. It will have 8 propellers, giving it the chance to fly into the titanium atmosphere and to fly around to different locations to then collect data and to try to understand geochemically what the surface is like, to learn more about the ices, to learn more about this organic gunk, and to search for potential signs of life. It could do that, even though it doesn't seem likely there would be life on the surface of Titan. There could be life down in a titanium ocean. If Titan has a liquid ocean down below, maybe there's life there, and maybe that ocean has some connection to the surface that we could find signs of that life. But again, the surface of Titan is extremely cold, so much so that the reactions that life as we know it require for biology to proceed aren't very likely at the surface of Titan. But it's always about possibility and probability. It's possible that life could be there, but is it probable? We don't know.
Yeah, totally. And the Dragonfly mission is probably one of my most favorites for this decade. Okay, let's talk about your work. What have you been doing in Borup Fjord?
Yeah, Borup Fjord Pass is a valley up on Ellesmere Island in the Canadian high Arctic. It's at 81 degrees north, 81 degrees west. This valley is unique in that it's one of the few places on Earth where we can find cold springs emerging from a glacier that are carrying with them a large amount of sulfur. There's one other place where this is really well known to happen, and it's called Blood Falls in Antarctica on the Taylor Glacier. In that case, there's a subglacial lake that's rich in iron and sulfur. The fluid is coming up through the glacier due to pressure on the lake below and emerging, reacting with oxygen in the air. And that oxygen reacting with the iron is making things like iron oxides, rust. And so Blood Falls is a reddish color. It looks almost like blood. If you see some of the really cool pictures and videos of it, it's incredible. But at Borup Fjord Pass, we have a different process occurring. So we have springs of fluid that are pressurized from the subsurface that are coming up underneath of this glacier, which sitting on top of the ground allows the ground to remain unfrozen. So permafrost in the high Arctic is extremely thick. The permafrost, the ground itself, is frozen very far down. But underneath of glaciers, there can be enough heat to allow fluid to flow through the subsurface. So that water, that fluid coming up, can then hit the glacier and can either drill through the glacier or come out at the very base of the glacier. And in our case, there's very little iron, and it's just very enriched in sulfur and hydrogen sulfide, that smell of rotten eggs. And when this hydrogen sulfide comes out in these springs at the surface, it also reacts with oxygen, and it forms yellow elemental sulfur. And so when you're flying over in a helicopter and you look down, I mean, it's incredible. When we first went to the site, I went there in 2014 and spent 2 weeks at this site in the Arctic, and we didn't know what to expect. It's very far away. It's very hard to get to. It took us a couple of days, 5 different aircraft to get there. And we were flying into the valley on our last helicopter to get into the site. And we look down and you just see this huge mat of elemental sulfur, this yellow sulfurous goop all over the place around the base of this glacier. And it's really stunning. And there are a few reasons that sulfur is really important for us. One is this site is considered an analog for Europa. Europa is one of the Galilean moons around Jupiter. And it's very well known for astrobiology because Europa has a very deep subsurface ocean. Down beneath a crust of ice that might be something like maybe 10 kilometers or roughly 6 miles or so, there could be an ocean down there as much as like 60 to 75 miles deep. So very, very deep. It would have more water in it than all of our oceans here on Earth. And so that gives us a lot of pause to think, could there be life in Europa's ocean? And if that ocean is communicating with the surface, if fluid from that ocean is making its way to the surface of Europa, or even making plumes that come out of Europa, can we look for signs of life in that material? And so having places like Blood Falls and Borup Fjord Pass, where we have fluids coming from the subsurface through glacial ice and then changing chemically at the surface, it allows us a little window into how we can prepare for looking for those things on Europa as well with upcoming missions. So that's very important. And also this site, those sulfurous materials are so enriched in sulfur that we expect the biology, the organisms, the microbes that are thriving in this system, in this ecosystem in the Arctic, to be reliant on sulfur biology. And indeed, what we found so far in a lot of the work that's been done by various researchers on the site is that a lot of sulfur metabolisms are involved. A lot of the organisms thriving here are utilizing this sulfur to make a living. And so it also helps us to understand the importance in sulfur just for life in general on Earth. But yeah, it's a very cool site. I was super fortunate to have a chance to go there. It's so far above the Arctic Circle when we were there in the summertime that the sun never set. It would just do a big circle around the sky throughout the day, and there was no night, which is really disorienting for us human beings. Like we grew to have some darkness in our lives to allow us to rest and to recover. And so I have to admit, we had these polar exploration tents that are intended to absorb sunlight, to absorb heat, to keep you warm in Arctic and Antarctic environments. But the tents were so bright that it was very hard to sleep. And I did have one evening where my colleague and I stayed up just to see the midnight sun in the sky, which was also a very cool experience. But yeah, I was very fortunate to go there to have a chance to do some exploration there, as well as to do my research then for my PhD on these sulfur springs, on this material and what's going on there. It was just a very cool experience altogether.
Yeah, I have some experiences of the long days in the Arctic. I mean, I live in Finland, and I've been to Norway where there's, well, the sun is up all night and it's difficult to sleep in the tents. But what would you think is the most viable planetary body in our solar system to have life other than Earth, of course?
That's a great question. And it's one that sometimes makes an astrobiologist feel trapped, because a lot of us don't want to just pick one thing. We want to do all the things. We want all of the funding. I want James Webb Space Telescope. I want the Life Mission Telescope. I want all the other next generation telescopes. I want all of the missions. I want more rovers and sample return from Mars. I want more sample return from asteroids and comets. I want to go to Venus and look and see if phosphine is there. I want to go to all the icy worlds, Titan and Enceladus and all these other places. I do have to say, I do have a warm place in my heart for Europa. I do think it's really worth our time to get back there and study. And the Europa Clipper mission, which will travel back to the Jovian system, it will do orbits around Jupiter and Europa together, but will give us much better resolution mapping and chemical understanding of the surface of Europa. It will allow us to really finally get a much better sense of how deep Europa's ocean really is. It can look for signs of potential life at the surface chemically. And then also, if there are plumes coming out of Europa, which we've had some Hubble Space Telescope-based detections of potential plumes coming out of Europa, much like they do in Enceladus. But Enceladus is a much smaller world. And if Enceladus can have hydrothermal activity, which we have chemical evidence for, in its much smaller ocean, then there's a good chance that Europa could have hydrothermal activity deep within its ocean as well. And so I think Europa's a really good place to go and explore for life. I wish that in my lifetime that we could get to Europa with submersibles, with drills that can drill down through all of that ice and take submersibles into that ocean. And there are people who are working on this right now. There are private companies and organizations like NASA and others who are working on figuring out how to drill through the ice and what we can do once we're in that ocean. My friend Brittany Schmidt, she's a very well-known scientist who spent a lot of time studying icy worlds in our solar system, and specifically Europa. She's part of a team that have developed the Ice Fin robot. They take this robot down to the ice shelf off of Antarctica and deploy it under the ice to explore the ocean below the ice, which we need more of that technology development and more planning for that. But technologically, drilling through 10 kilometers of ice will be very challenging. We don't have any place on Earth where there's 10 kilometers of ice in thickness. Our thickest ice sheets in Greenland and Antarctica are nowhere close to 10 kilometers in depth. And so for us to drill through that on another world so far away without support and the ability to replace parts if they break, it will be a very large technological undertaking. But it's one that I think is definitely worth our time.
And what do you think the chances are of life on all-water planets such as Kepler B22?
Yeah, so, again, like in my lifetime alone here, we've now discovered thousands of exoplanets, and that number is going to continue to grow, especially with some of our other upcoming next-generation space telescopes. We'll start discovering even more of these alien worlds. But thus far, we've been very limited by the kinds of worlds we can find. So you've heard a lot, like early on, we mostly found these giant hot Jupiters, we called them. They were very large gas giant worlds, very close to their stars. The reasons that they were easier to see is since they're closer to their star, they can block more starlight. They can also cause more wobbling since they're nice and close and they're very big. But it's also the period of their orbits is very small. And that means that we don't have to observe them for very long to have enough data to say that there's a planet there. But some of the other worlds that are further away, worlds like our Earth or worlds like our Jupiter at 5 AU away from our star, and even further out, worlds like Uranus and Neptune. For those worlds, for those detections, we really need a lot more time to have these worlds have time to orbit around their stars and come back around again. So we've only touched the tip of the iceberg in what's out there in exoplanets. There's an astrophysicist named Nick Schneider. He's a professor in astrophysics at the University of Colorado in Boulder. And I took a class with him many years ago in planetary science as Kepler was collecting data and finding thousands of more worlds. And he said, like, one thing that a lot of them discovered early on is that everything we thought planets couldn't do, we keep finding with finding new exoplanets that they're doing it. Even the finding of hot Jupiters. At first, we didn't think the gas giants could be found close to their stars. That made us go back and try to figure out, why are large worlds able to be so close to their star and have yet this mass of gas around them? It doesn't make any sense given our knowledge of planetary formation. It made us rethink how planets formed in our own solar system. And so we're going to learn so much more along the way, not just for us astrobiologists looking for potential life, but we're going to learn so much more about how worlds form around stars and the history of our own solar system just by finding exoplanets and learning more about how they form and the processes that occur on them. But when it comes to finding alien life, I think that this sheer number of worlds out there, it makes it so much more likely that we're going to find life at some point if it is out there. And we're going to find a lot of worlds like Earth. We're going to find terrestrial worlds. They may or may not be the best place to look. Maybe we'll discover signs of biological activity inside of some of these gas giant worlds around other stars. Very famously in the original Cosmos series with Carl Sagan, Adolf Schaller created some very beautiful artwork to go along with Sagan's suggestion of what alien life might be like in a gas giant world like Jupiter. Could there be giant floating sacks of alien organisms with others that have wings and all kinds of evolutionary features to allow them to survive inside of gas giants? We don't know. Maybe icy worlds, maybe ocean worlds like Europa and Enceladus and Titan here in our solar system. Maybe those worlds are the ones that have far more life. And if that's the case, it could be actually rather saddening. One, because it's harder for us to actually find those worlds. It's going to be some time before we start finding icy ocean worlds around planets and other solar systems. But even then, if life forms in a biosphere inside of a subsurface ocean, that life might never even have contact. It might never even see the stars out beyond the surface. And Kevin Peter Hand is a very famous scientist at JPL, also a great researcher in icy worlds, including Europa. He's involved in the Europa Clipper mission. He recently wrote a book called Alien Oceans, which he goes into the science of how we understand that there are oceans on worlds like Europa, and also what we were looking for potential signs of life. And he has a really great chapter where he considers what would it mean for a biosphere to develop on a place like Europa, and then even more so for intelligent life. If it's possible that intelligent life could form inside of an ocean world, what would that mean? What would their understanding of themselves be like when they can't see the stars, when all they know is the biosphere inside of that ocean, and it has a lid, a crust, containing it inside of that world? If it were possible that an intelligent civilization could exist in such an ocean, man, they would have to be so different from us in how they think of themselves. And so I highly recommend that book. It's a worthy read, and it makes you think a lot, too, about what it means for us in our place and time in the universe, for us to look out and see the stars and to see what we have around us. You really do have to consider that alien life might be very different.
Yeah, that ties perfectly back to the Kepler B22 question as well, because that's a water world. So I will definitely link that under this podcast and YouTube recording also.
Okay, at this point I would like to ask our viewers, do you have any questions you'd like to ask live?
Well, thank you for the opportunity. First of all, awesome presentation, lots of energy. So thank you so much for passing by and teaching us some of the insights you have. Maybe a small question here. I've been watching this subject for a while lately. I'm not a person from the domain, but yeah, I'm trying to keep up to date. So I've seen a few debunk videos, and most of them complain about the really low ratio of parts per million, or even lower than this, for the phosphine gas. Any comment on this?
Yeah, so I could get this wrong, so definitely go back and check the data. I feel like it was 20 parts per billion was the upper limit in that paper. I could be wrong there. It is very low. That number is extremely low. And we're kind of in the same boat when looking for things like that cyclopropylinidine in Titan's atmosphere. If you read that paper with lead author Connor Nixon, they're also looking down in this parts per billion level for concentrations. And they are using ALMA as well for that detection. ALMA does have the resolution to allow us to see molecules at the parts per billion resolution. And so I'm less concerned about that. Honestly, when it comes to whether or not phosphine is on Venus, the amount of phosphine, if it was like parts per million or parts per thousand, that would make me really question the analysis, because that would be a lot of concentration for a molecule that really shouldn't be in that kind of concentration. But at the parts per billion level, I mean, that really doesn't mean that there's a lot of it. There's actually very small amounts of it then in the atmosphere of Venus. And so much like for our atmosphere, we talk about nitrogen and oxygen, but there are, parts per billion gases in our atmosphere as well. And so when it comes to the limit, I don't find that as questionable as I find myself just wanting a confirmation of the detection.
Yeah, that's definitely an interesting debate here to have. A small note, and then I'll let everybody else ask questions. So I'd love to invite you for a separate discussion on Nexora. I'm not sure if you ever heard about this project. It's a enthusiasts community that want to design habitats for Mars. So we would like to hear your thoughts about the possibility of finding maybe even like proof that there was life on Mars. How would that impact everything, and what would it mean, and what would we expect from like the governments to undertake as actions and so on. So if you want to comment on this, that's great. And if you want to get in touch afterwards, that would be massive. So thank you.
Yeah, thank you. And both are awesome. Yeah, let's talk later. So I've been an analog astronaut. I went on a crew rotation at the Mars Desert Research Station, which is a Mars analog base for here on Earth in Utah. We actually have Mars analog bases all around the world now. There's MDRS in Utah, there's FMARS, and the Houghton Mars Impact Research Station up in the high Arctic. There's High Seas in Hawaii, there's DMARS and MMARS and several other Mars habitats around the world where humans are trying to explore not only what will it be like for us to be on Mars exploring, but also gives a lot of us a chance then to while wearing spacesuits and while using rovers to explore how we look for signs of life on Mars. I also helped to run an undergraduate engineering competition called the University Rover Challenge. We have teams from around the world, from the UK and Poland, the US, Canada, India, Bangladesh, Egypt, just all over the world who spend the better part of a year in their academic studies developing and designing and building Mars rovers. And then they go through a selection process with us to make sure they're prepared. And the teams who are most then prepared, they actually come to the Mars Desert Research Station in Utah in the summer. And we have a 3-day competition where we have the teams. We test the teams as well as the rovers in a mock simulation of what it would be like for the rovers to be active on Mars, including look for signs of life. And I've seen some really, really smart things these young students have done over the years to try to complete our tasks, including looking for signs of life. And so I can always talk about looking for life on Mars, and also keep up with the news with the Perseverance rover. It's going to land mid-February on Mars. There's a lot more great science coming from Mars exploration.
Thank you so much.
Great. Looks like that's all the time we have today. Graham, could you tell us where people can find you?
Yeah, absolutely. My website is cosmobiota.com. That's COSMOBIOTA, Cosmobiota. So biota is a word that means living material, living matter. When we go out as biologists looking for life, we might be looking for biota in various places. Cosmobiota is a term that I created for the living matter of our universe. You can also find me on Twitter and Instagram at Cosmobiologist, on LinkedIn and Facebook at Astrobiologist, since I was the first one there. And then I'm always happy to chat with people. Feel free to reach out. I am a member of Blue Marble Space and the Blue Marble Space Institute of Science. And I love having conversations about space exploration, about the cosmic perspective, about what it means for us as humans in this point in time right now to potentially be capable of discovering that we're not alone in the cosmos.
Thank you. It's been a great session with you. Thank you very much for coming. And I've been Mikko, the host of Deep Dive Friday.
I've been AnotherSpaceNut. I just want to say thank you today, Graham, and thank you, Eavesdrop listeners.
And thanks for having me.